Nothing beats. This video, we're going to come up with the derivatives of the sine and cosine functions. Let's go. All right, here's our goal right now, right? Come up with the derivative of sine of x with respect to x and the derivative of cosine of x with respect to x. We'll start with the sine function here. So, just as a reminder, here is graph of the sine function. Let's say f of x is sine of x right here. Now, we see that this function, of course, is nice and continuous. It's nice and smooth. No corners, no holes, no asymptotes, and of course it's periodic. So for that reason, we should expect its derivative to be defined for all real numbers, first of all, and also for its derivative to also be periodic, since the slopes of the function repeat themselves over and over regular intervals. Now, what I'm going to do is I'm going to pull up a picture here. So here's the sine function once again. But now we have a little dynamic situation going on here. So as we move through, we can see the line, the tangent line, changing, and we see it right there, right? Up here is the actual value of the derivative of the sine function. Now, right here at negative pi over 2, we're just so close. We're just barely right next to negative pi over 2, and we see how tiny it is. Now, at that location, we should expect the slope to be 0 since the horizontal tangent line is happening there. Moreover, we should expect it to happen at pi over 2, right? Right around there. You see it gets really, really tiny. And at all of these local extrema, right down there as well, we should expect slopes of zeros at all those locations. So go back to the graph over here. You know, we think if we start kind of drawing in the picture of the derivative of the sine function, well, we should expect right here, I'm drawing a little dot, that the derivative in green will be 0 at negative pi over 2. It'll be 0 at pi over 2, 0 at 3 pi over 2, 0 at 5 pi over 2, 0 at 7 pi over 2, and so on and so on and so on, right? The slope of the sine function is 0 there because the tangent line will be horizontal on the graph of the sine function. So you start thinking, that kind of seems like maybe there's some type of cosine related to this. So what is this function that we're after here, the derivative of the sine function? Going back to the figure over here, another thing that we want to take notice of is where does this derivative of sine seem to take on its biggest and smallest values? Well, let's go all the way here to the left real quick. We know that over here at negative pi over 2, we have a slope of 0. Now, from negative pi over 2 to pi over 2, sine function is increasing. So we're going to see that the slope is going to be positive. And moreover, since at negative pi over 2 the slope is 0, we should expect that the slope gets larger and larger throughout this interval, but then eventually gets tinier again as we get close to pi over 2. And in fact, as we move the little slider along here, we can see the numerical value up there of the slope getting bigger and bigger, and then eventually right around x is 0, the slope seems to get really, really close to 1. And then as I keep moving over and get closer to pi over 2, eventually gets to 0 again. Moreover, from pi over 2 to 3 pi over 2, the sine function is decreasing. So we should expect the slope be negative, and we can see right away we're a little bit to the right of pi over 2, and the slope is negative. And as I move through the interval pi over 2 to 3 pi over 2, we see that the slope again becomes more and more negative and seems to obtain its most negative value right at pi, which seems to be a negative 1, before we start getting closer and closer back to 0 as we get to 3 pi over 2. So it sure seems that at 0, the slope tends to be maximal of 1. At pi, the slope seems to be the most negative, which is -1, and then it's going to repeat like that as we move through the sine function. So over on our graph, we should expect that at x is 0, the derivative should be about 1. At pi, the derivative should be -1. At 2 pi, slope be 1. And at 3 pi, the slope is, whoops, I put that there, right there at 1. And then at 3 pi, the slope to be -1. So you kind of piece together this graph, you kind of see the shape of it. It sure kind of seems like this looks like another graph that we know. Looks like a cosine graph, does it not? So we should maybe start hypothesizing that perhaps the derivative of the sine function might be the cosine function. Seems like that's true, right? What we just said, the derivative of the sine function is the cosine function. Now, it doesn't show it to be true, but it sure seems like it. So what we'll do is we'll actually show it to be true by using the limit definition of the derivative. So let's do that. What we will need is a couple of formulas to help us along the way throughout this derivation, one of them being the sine of the sum of two angles. So recall that this is an identity from the topic of trigonometry. If I have, say, the sine of alpha plus beta, then that formula is sine of alpha cosine beta plus cosine alpha sine of beta. Okay, so we got to recall that. And then we have a couple limits, which we're going to do a little bit of hand waving here. These two limits right here. The claim is that the limit as x goes to 0 of sine of x divided by x is 1, and that the limit as x goes to 0 of cosine x minus 1 divided by x is equal to 0. Now, these limits can be shown to be true using something that we have not come up with yet, which is called the L'Hopital's rule, which we won't talk about right now, but it's very easily shown using that rule. And it can also have some type of trigonometric identities and geometric approaches to show that indeed these two limits are true. So for the time being, you're just going to have to say it's true, and if you don't believe it, go prove it, because it can be proven. So these three formulas we will use within our derivation right now. Okay, so let's get to it. By definition, right here, the derivative of the sine function sine of x with respect to x is the limit as h goes to 0 of sine of x plus h minus sine of x over h, right? That's our limit definition right there. Now, what we're seeing in this step is our sine of a sum, right? So earlier we had sine of alpha plus beta, but right here we have sine of x plus h. So we can apply the sine of a sum formula to that term, and we get sine of x times cosine of h plus cosine of x times sine of h, right? Just applying that identity. So that's where we see this next step in this limit. That's where that comes from. And then in this step, what I'm doing is I'm just grouping together the sine of x terms because we're assuming this limit exists. It sure seems that way, right, based on the graph of the sine function. I can apply the sum of limits. First of all, right, we see two limits here, right, split up as a sum. And then all I did was take the sine of x cosine h and the minus sine x and threw them into that first limit. And then I'd be left with the cosine x and the sine of h on the second limit. Right, so I'm just splitting up the terms in this way because here there's a common factor of sine of x. So I'm going to take that sine of x out in front of the limit. And again, I can do that because h is the variable that's changing in the limit, not x. So sine of x acts like a constant within the limit. And what I'm left with after factoring out the sine of x terms is cosine of h minus 1 over h, that limit. And then over here on the second limit, I also took out a cosine x just because I can, because again, the cosine of x acts like a constant within the limit since h is the variable that's changing in the limit. And then so what we're left with is these two limits that, remember a moment ago, we talked about what those limits actually are. And that was that the limit as h goes to 0 of sine of h over h, that was equal to 1. And the limit as h goes to 0 of cosine h minus 1 over h is 0. And as we can see, if we apply that formula, we get that exact thing I just said. And of course, that simplifies to cosine x. And that's exactly what we thought the derivative of the sine function should be. And thus, we conclude the derivative of sine of x with respect to x is cosine of x. Add it to the list. Add it to the list. So we got another one down. But what about the other function? We're also after the derivative with respect to x of the cosine of x function. So recall, here's our cosine function, right? Now we know it's also the derivative of the sine function, and we can play a similar game that we played before. And in fact, I have another figure for the cosine function here showing its slopes. And since remember also that the cosine and sine functions are just shifts of pi over 2 units from each other, and so that whole discussion that we had about, okay, at the local extrema, right, there should be slopes of zeros. So right here at x is 0, we should expect the slope to be 0, right? Gets really close to 0. At pi, we should expect the slope to be 0. Right down there, horizontal tangent line, and so on and so on, 2 pi, 3 pi, and whatnot, keep going. And so we'll start drawing that into the graph. I'll use red here, and the red will indicate our construction of the derivative of the cosine here. So we know at x is 0, the slope should be 0. At pi, the slope should be 0. At 2 pi, the slope should be 0. 3 pi, the slope is 0, and so on and so on. And you might start thinking, oh, well, a sine function has zeros at those locations, but is it actually the sine function or is it something different? Well, that's why we go back to our figure here and notice something. Notice that at these locations, negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2, and so on, those are those locations for which we will have maximal slope in magnitude. At pi over 2, the maximal negative amount, and negative pi over 2, maximum positive amount. And remember, just by looking at it and estimating, we can see, negative pi over 2 sure seems to be a slope of negative 1, right? And at 3 pi over 2, let's go over here, right over here, about 3 pi over 2 slope is about 1, and so on and so on. And so we start constructing that part of the graph. All right, at negative pi over 2, we should expect the slope to be positive 1. And at pi over 2, we should expect the slope to be negative 1. 3 pi over 2, the slope to be positive 1 again. 5 pi over 2, negative 1, and so on and so on. And we start piecing together the graph here, and we get a picture that looks like that, right? Something like that. Now, it's not exactly the sine function, right? Because the sine function, starting at x is 0, increases to 1 first. But here we see it's decreasing. But if we just take note, if I were to reflect that red graph about the x-axis, I would get exactly the sine function, like so, right? And so on and so on. And thus, we may suspect that the derivative of the cosine function is actually not sine of x, but perhaps negative sine of x. That's our hypothesis here, right here, just by inspection. Now, we could go through the limit definition again, state a few important formulas, do that whole game just like we did for the sine function. And it ends up that it is true, and you can do that proof in a similar way that we just did for sine of x derivative. So hopefully you'll just say, I bet it can be done, and that indeed is true, and thus what we do is we conclude here that the derivative of the cosine of x function with respect to x is negative sine of x. And now we have the derivatives of the sine function and the cosine function, and we can do more things. So first we're going to find some derivatives here. Actually, we'll do some derivatives and then that'll be it. Let's just find some, okay? Just practice what we just figured out. In part A here, let's find the derivative with respect to x of e to the x times sine x. So I got a product here. Have to apply the product rule. So what's this going to be? E to the x times the derivative with respect to x of sine of x. And then plus sine of x times the derivative with respect to x of e to the x. Differentiating, we get e to the x. And then remember what we just figured out. Derivative of the sine function is the cosine function. So e to the x times cosine x plus sine x. And of course, the derivative of e to the x is e to the x. So I get a plus e to the x times a sine x, or if you prefer, e to the x times the sum cosine x plus sine x. So there's our first example. Not too bad, as long as we remember what the derivative of the sine and cosine functions are. Let's do another one. How about this one? The derivative with respect to w now of cosine of w minus w times sine of w. So first take note that this is the same as ddw of cosine w minus ddw of w times sine of w. So I'm just using the difference rule for derivatives in that first step. Now, the derivative of the cosine of w with respect to w is, of course, negative sine of w that we just concluded. So this is going to be a negative sine w. And then minus, well, I have a product rule again, right? The derivative of w times sine of w with respect to w. So I got to apply the product rule. And because that minus sign's out in front, I got to remember to keep that minus sign attached to my entire product rule. So maybe in brackets here, we'll write, all right, product rule, w times the derivative with respect to w of sine of w, and then plus a sine of w times the derivative with respect to w of w. Let's finish it off. What do we get? All right, we got negative sine of w minus the quantity. Derivative of sine of w with respect to w is cosine w. So I get w cosine w. And then the derivative of w with respect to w is just 1. So I'm left with a plus a sine of w. And then cleaning this up, distributing, we have a minus 2 sine w and then minus a w cosine w, right? Just distributing the minus sign and collecting the like terms. And there you have it. There's another derivative. So as long as we remember what the derivative of cosine w and sine w is, with respect to w, of course, then this is just the same thing that we were doing before with product rule. Just got some new derivatives that we're looking at. All right, last one before the end of this video. Now this one looks a little daunting at first because we're asked to find the 527th derivative of sine of x with respect to x. So one might say at first, you're going to really differentiate sine of x 527 times? I guess you really could, but instead we want to see something special happen here. And that is that it ends up that the derivatives of the sine and cosine functions are cyclic in nature, meaning that they end up repeating themselves. Let's take a look. So for instance, the very first derivative of sine of x is, of course, cosine x, right? So there's our first derivative. The second derivative of the sine function with respect to x here is the derivative of cosine x, what we just found, right? The second derivative, differentiate twice, and we get negative sine x. How about the third derivative? Third derivative of the sine function with respect to x is, well, take the derivative of the second derivative now. That's the derivative of the negative sine function, which is the negative cosine function of x. And then the fourth derivative of the sine function with respect to x, well, that would be the derivative of the third derivative, which is the derivative of the negative cosine of x right up there, which is a negative sine x, which is sine x. And as we see, we're right back to where we started. So if I were to then find the fifth derivative of sine of x, it's just going to be the same as the first derivative as the sine of x. The sixth derivative of sine of x would be the same as the second derivative of sine of x. So really, this cyclic pattern shows us that we can use what's called modular arithmetic here to say that, okay, well, if I really want to find a 527th derivative of sine x, all I'm going to do is divide that 527 by 4 and see where in this cycle we actually end up, because we just keep going through the cycle over and over and over again, and eventually once we get to the 527th derivative, it's going to be one of these four things. So old school style, 527 divided by 4 here, since I don't have my little calculator next to me. Let's just do it this way. All right, 4 goes into 5 once. Subtract that. 4 goes into 12 3 times. 4 times 3, of course, is 12. And subtract that. We're left with the 7. 4 goes into 7 one time. And, of course, 7 minus a 4 leaves us with a remainder 3 here. All right? 131 remainder 3. Now, we don't often write this as remainders, since usually we write it as a fraction or a decimal when we do such a division here. But the remainder is really what we're after, right? Because it tells us, okay, what happened here? If I took the 527th derivative of sine x, what I really just did was I went through this entire cycle that we see above 131 times, and then I went to the 1, 2, 3rd derivative here. So thus what we're saying is that the 527th derivative of sine of x with respect to x is really just the same thing as the third derivative of sine of x with respect to x. And of course, we already figured out what that was. It was negative cosine x. And there you have it. So something similar can be done when differentiating very high order derivatives of the cosine of x function. You would just end up in a slightly different spot than what we were right now. So that's it for the video. What we're going to do in the next video is we're going to take the results from this video, the derivatives of the sine and cosine functions, and then we'll use that to find the derivatives of the other trigonometric functions, the cosecant function, the tangent function, the cotangent function, and the secant function. And until that time, it's Math and Beats, and I'm out of here.